Hi everyone, thank you so much for coming. This is AI School 2. Today we're going to be learning about gradient descent, perceptrons, and activation functions and neural networks. So thank you so much for coming. Please raise your hand if you need any help, like always. And I'm going to pass it off to Malcolm.
Oh, wait, it's my turn? All right, can everyone hear me at a reasonable volume? The two guys in the back, can you raise your hand if you can hear me at a normal volume? All right, okay, so I'm supposed to come up with an icebreaker. Normally that's Saunders' job, but he's I don't know what's up with him today, so I gotta do it instead. Check it out. There and okay. Alright, so let's do some random icebreakers. What's your favorite programming language? Someone give me their favorite programming language. Is that right? Python? Alright, does anyone here not like Python? Why do you not like Python?
I think it's slower, and I'm more used to Java, and I'm going to just know Java. But I use Python that maybe it isn't.
There's a whole long secret around the grades. Often really hard to use the different model on this. So if you see something in the laptop, don't immediately does it for being a game, even though that's a perfectly respectable thing. Maybe they're just making a deep learning model. Alright, but one of the disadvantages of doing that on your own laptop is it wastes a lot of power, and then you're also like venting a bunch of heat on like part of your laptop fans. So usually people will like rent a GPU from like AWS or something and pay on that instead. And then Amazon can take care of like all of that. Alright, I think the ice has been sufficiently broken, especially because with climate change, the ice is weaker anyway, so it's a lot easier these days. So we will start on the actual technical content, which is definitely why you are all here, and not for the three bonnies in the back. All right. All right. Okay, so 2 weeks ago, we did workshop 1, which was fun. Jupyter/Coda, plus NumPy, plus Matplotlib, which isn't really like AI specific, but it's still important because when you want to implement stuff, you're going to be using these tools, and being good at these tools will make it so you don't have to like waste all your energy and time trying to figure out some obscure like programming trivia, and instead you can just worry about your model, like your artificial intelligence. So now that we got that out of the way, we're going to start on workshop 2, which is gradient descent and neural networks, which is like the shiny stuff, like the stuff that everyone wants to hear about. Wait, how do I go forward? Oh yeah, and by the way, the checking code is second school, so make sure to put that into your ACM account to get free points. And with those points, you can buy a lot of cool ACM merch like Sombert's wearing today. Come on, show him Sombert. Show him the front and the back. It looks so good. Yeah, this one's one of my favorites. It's the dark mode one. All right. Okay, so the high-level overview of today's workshop is we're going to motivate why you like need this idea of machine learning and machine learning models, and then we're going to talk about how those models learn by gradient descent. Then we're going to introduce essentially like the core model, the core of many of the models that are in use today, which is the perceptron. So that's like the most basic neural network. And we're going to talk about some parts of the neural network, specifically activation and loss functions. And then after that, we're going to work on a specific concrete example, which is training a neural network to classify numerical digits. So like you show the picture of the digit, and the model will tell you, is it a 1, is it a 2, is it a 3, is it a 4? I could go on and on, is it 5, 6, 7, 8, 9? I guess I just did. Anyway, that's going to be part 5. This is the part with 11. Yeah. Any questions so far? All right. Okay, part 1, machine learning. So the reason we need machine learning is that a lot of the time we're solving problems for which development of algorithms by human programmers would be cost prohibitive. So the idea here is that a lot of problems you want to solve in the real world, it's very hard to come up with an explicit program for how to handle each case. So like one like very practical example is object detection. Say you want to like take in like a bunch of images and you want to draw boxes around all the interesting objects in that image, like this dog and this bicycle and this van. It's very hard to write a program, whatever programming language, it's very hard to write an algorithm that can do that already. Like, sure, you could be like, oh, a dog is always like roughly this big, and like the van is always gigantic, but what if the van is in the background? Now it's tiny, and like how would you even describe the dog? And like in your head, you have this idea of like, oh, a dog looks like this, it has like ears and tails and paws, but you have no way of encoding that inside a program. So in order to get around that problem, we use machine learning. And with machine learning, what we do is instead of having a human use their intuition and logic to write like explicit rules for how to solve a problem, we instead use training data. The idea here is that you have a bunch of examples that you show to the model, and the model will learn its own rules based on those examples. So you don't write your own rules, you just give it a bunch of examples, and then the model will kind of figure out some pattern that will fits to all those examples. So in the previous, so in this example right here, what you would do is you would show it a bunch of pictures, and each individual picture would contain a dog. And the idea is you would have some poor human draw boxes around every single dog in every single picture. And that way, and then you would show that entire data set to the machine learning model. So essentially what you're doing is you're distilling down the human like intuition from the person who drew all those boxes. You're taking that intuition and you're somehow distilling it into the model, so the model can draw boxes around new pictures with new dogs. Is that clear so far to everyone? I heard one yes, so that must be good enough. All right. So in our dog detection example, the input would be just the image. So like, there'd just be like a bunch of pixels, like a JPEG image. And you would pass it through this model, which we will cover later. And the hope is that this model will be able to give you the corners of the box. So it would be like, oh, like the lower left corner is at like this coordinate, and the lower right corner is at this coordinate, and the top right corner is at so-and-so position, and so on. The idea is the model would output like these 4 corner positions, and ideally, those 4 corner positions draw out a box that contains the dog. And when we train on training data, what we do is we take an image that a human has already drawn a box around, and we like, probably draw an example. Okay. So everyone see this box. So this is your image. It's like a grid. It's a giant grid of faces. Okay. And somewhere there's like there's a dog inside. This is the cute dog. So the idea is we have a human draw a box for you. And this box with its 4 corners, this is called the ground truth. This is like the correct answer of where is the dog inside the space. And this ground truth we usually call the label. Then what we do is we pass only the image. We don't give it this ground truth answer. We only pass the image into our model, and the model will output its own box, which will look it'll be kind of long, but it won't quite get the dog inside the box. Then what we do is we compare the model's prediction, which is this like not quite right box. We compare it with the ground truth box, and then we define a loss function, which is like a single number that describes how good the model's prediction is compared to the ground truth answer. And the idea is that we minimize this loss function so that the model's prediction is actually really close to the ground truth. And usually we denote it as L, Y hat, and Y. So here what we're doing, so the L stands for loss function, and we're taking the loss between the model's prediction, which is called Y hat, and the ground truth, which is called Y. So one more like really like simple example is like say you want to model like a linear function like y equals mx plus b, right? So the goal when you're modeling something like that is you have okay, I probably can't write it in the memo, okay. So the goal is you have this y equals mx plus b, and depending on what you choose m and b to be, you can make that line like literally like any angle, any direction, any position. Like that line could be like literally anything on the Cartesian plane. And your goal is to choose the correct m and the correct slope and the correct y-intercept so that your line fits whatever data you have. So in this case, like what you're trying to learn is the slope and the y-intercept. And in a more general case, when you're more general case, the things you're trying to learn are called your parameters. So you might have heard like, oh, like these large language models have like 100 billion parameters. And in that case, you're literally trying to learn 100 billion different numbers so that like your large language model can do whatever it's asked of them to do. And for something like learning like a straight line, like the y equals mx plus b, you usually use a loss like least squared error loss, which is just the difference between your prediction and the ground truth squared. And it's equivalent to that equation. Okay, any questions so far about like what we're going to do on that? If anything is confusing, please ask us. Okay, so we have our model, we have parameters that we're trying to learn within the model, and the question now is how do we actually choose the correct value for those parameters? Because like if you were training like a gigantic model with like millions of parameters, like you can't just like try every single value for every single parameter, like you'll never finish. So the answer is we use gradient descent. So the idea behind gradient descent is that we basically like walk down the hill of the loss. So this like landscape right here with like this like high area, this low area, these valleys. This is called the loss landscape. So the idea is it shows how well your model is performing for like every possible setting of the parameters. So like going back to our like getting a straight line example, you have y equals mx plus b, right? The input is your x, and you want to learn the m and the b. So we have for our horizontal axes, we have the m and the b. And now your task is to find the correct m comma b pair in this entire horizontal plane that will minimize this loss. So the answer is like somewhere down here or like here, on these values. So the question is, how do you find those values? Like if you don't know and you only have training data. And the answer is you just randomly initialize your model. You start with a random value for your slope, you start with a random value for your y-intercept, and then from there you use gradient descent. What gradient descent is doing is at every point, wherever you are, you calculate the derivative around you. So the idea is the derivative here is the derivative of the loss with respect to your parameters m and b. So the intuition here is if you wiggle your parameter value by a tiny bit, if you change your m by a tiny bit, how is the loss going to change, like as a consequence? And same with the b. If you wiggle your y-intercept a little bit, how is your loss value going to change? Is it going to go up? Is it going to go down? Is it going to stay the same? And you can encapsulate that information inside the derivative of the loss. And then, assuming you can calculate the derivative of your loss, then you just keep walking in the direction that decreases the loss. You just keep going down and down and down and down, and eventually you'll get to one of these values. So a very like common like picture people draw when talking about this is they'll draw like a very like minimal example, which is like we'll have some curve. Can everyone see this? You'll have some curve like this, and you'll be like, oh, like I want to like and the y-axis is your loss. You want to be like, oh, I'm going to find whichever like parameter value minimizes your loss. And like, it's gonna be down here somewhere, like you want to get here. But like, let's say you start like, let's say you like start over here, you have a pretty high loss. So clearly, like you're all here, you probably know some calculus. You take the derivative of this, and the derivative tells you like, oh, the slope is like positive, right? It's kind of like steep and high and positive. So you walk this way, you walk down the slope, and eventually you get like here. And then you say, oh, well, the derivative is still positive. I'm going to keep walking in the downhill direction. You walk again, you get like here. And then you keep walking, and eventually you get down to like this part right here. And then you try it again and say, I want to walk in the direction that like, makes me go downhill the most. But you're already at the bottom, like as far as you can tell. You can only see like in this like small region. Like that's all you can understand as you're doing gradient descent. So you try walking and you're like, oh, I'm already at my like final destination, and then you're done and you stay here. But actually the best answer might be over here. So gradient descent is a greedy algorithm in that sense, where at every step you take what looks like the best possible answer, but like only in a lower region around. And sometimes that can give you like suboptimal solutions, like this guy. Like it's pretty good, but it's not the best one. Like the best one's over here, but you have no way of knowing that it's over here because all you can see is like this narrow slice. Does that make sense, everyone? Okay, I need like an honest answer. Does it make sense in the sense that you actually know what I'm talking about, or is it like I have no idea what he's talking about, so I'm gonna like not say anything? Because I had a feeling.
This is the best explanation I have ever received of gradient descent, so thank you.
All right, is it the only explanation you've ever received?
It's not the only one, so we have something better than this.
Thank you. It's nice sort of validation for myself. I don't get much of that these days, so I'll do it. Yeah, okay, so that's the basic idea of gradient descent. And we're doing the same thing here, except now you can walk anywhere on like your horizontal plane. So like if I was doing gradient descent right now and like this like z-axis with my loss, right? I want to get as low as I can go. As low as I can go. And let's say I started like looking. The loss is like kind of they're kind of high, right? So first I'm gonna be like, what around me like will take me to the lowest loss. If I try to go this way into the wall, right? And I hit like undefined loss, like I just go all the way to the ceiling, but like hella high loss, I don't want that. So I go down here. I'm like, okay, what around me is good. If I go back here, I'll go up in loss, which is bad. So then like I look around, but it's actually flat, which is actually a problem when machine looks like when you're doing gradient descent. If the loss landscape around you is flat, then like even if I walk this way, it doesn't help me, right? So sometimes like you're trying to train something, you'll just get stuck in like this flat thing where like you don't improve, you're just kind of walking along randomly, you have no idea. And because it's gradient descent, because it's a greedy algorithm, I have no idea like about the global like loss lines. I can't see like all of you, for example. I can only see like this tiny radius around me. But if I keep walking, eventually I'll hit like these stairs, right? I'll be like, oh, like this takes me low. So then I'm one, go down two. And now I'm not like move off and
So when you do gradient descent, it's only like a certain slice or a certain radius, a certain area. Does it perform it like several times then to compute the lowest loss?
yeah, so you like take these steps like over and over and over.
Yeah, it's like you repeat it into the line.
And you repeatedly, but each time you're trying to lower the loss a little more. And usually you stop when like you just been doing it for a long time and the loss is like that's very limited. And usually that means you found like a pretty good solution, like a pretty low loss area.
There's
No. So like this kind of goes back to the you only like it's a greedy algorithm. So like you can't see this whole landscape. At any time you can only see like a tiny area around you. So it's not a brute force in that like you're trying every single like possible like slope and light intercept value and like evaluating all of them and then going to like the lowest possible value. Like you really only see like this path that you walk along, like that's all you ever see. So like as far as you're concerned, like that's all you have to go on. Like you can only choose the lowest loss within like that path. Like all this other stuff, like over here, and like over here, and like over there, like you never see that, and you have no idea. Like there could be an amazing solution with super low loss, like somewhere there, you just never see it.
Most that comes first, or these programs to make. And this is the employee build option for it, and then try to see if there's.
That's a good question. So gradient descent, like the vanilla version, like the most basic version that I just described to you all, it will get stuck at the first like the first decent solution comes. So like the moment it hits like this like little dip right here, it'll be like, oh, this is clearly the best solution because like I can only see like a tiny radius around me. I have no idea about the rest of the world. And especially because it forgets everything at the stop. Like it really only like it's super greedy. It only cares about what it can see like right now at this moment. So if it sees like this like decent solution here, it'll just stop. It'll just give up and quit. But like there are like various modifications and various like practical considerations that make it so that sometimes like if you get to like this like decent solution but not perfect, it will actually like jump out of this like little dip and like keep surfing. And like that is a thing that like you do in practice. Yeah. But like other times you might get stuck. Like if you get stuck here and like you don't have the right modifications to get on, then you're kind of screwed. You're out of luck.
But if you change where it started,
if you change where it started,
so like compare the two or not.
yeah, if you do that, like you can't do that, and if you try a bunch of different starting points, like you'll probably and you try all of them, you'll probably get a final like better solution, but then you have to try all of it. And that means working on like, you have to take the time, like burn the resources to like try all of them. Any more questions? So this was a very simplified example. I can visualize it here because I only have two parameters which I'm trying to learn. In practice, there's millions or thousands or billions of parameters. You cannot visualize the plot like anymore. It becomes this like super high dimensional thing that you like need like 1 billion IQs to like visualize. It's just impossible. Maybe Sonder, if you do it, you can do it. I believe in you. All right. Okay, so this was like a picture I found, like kind of showing like some more intuition about it. So the idea is that like this is your loss landscape. This is like a mountain, so like you would kind of need something to find the peak here. But when we're kind of minimize loss, what we're actually trying to do is find the lowest point on this landscape. Yeah, but the reason I chose this picture is that is to like get you used to the idea that you can represent this 3D landscape, this 3D view of land. You represent this like on a flat plane. You just like have all these like elevation contours. I mean, you've probably seen this before. It's like every line represents like a certain elevation, and like the highest point is actually in the center, like all the way up there. Does that make sense? All right, cool. So the reason I show that is that we can use that same example for our learning a linear function. So here, like the x-axis would be our slope, and our y-axis would be the y-intercept. And our loss landscape looks something like this. And we're trying to find the lowest point in, so like the z-axis here is actually our loss, and we're trying to find the lowest point in our loss landscape. So it would be at the center of this like parabola. But you can redraw this whole thing like this. And then like the center of your like bowl is like right here. And just as you were trying to walk down the curve of that bowl, now you're also walking down like the curve of this like parabola, but you're doing it like in this like elevation like representation. And the key here is that when you're doing gradient descent, you're actually like you're changing your parameter values by a tiny bit. Like you're changing your slope and your y-intercept by some like small amount in the direction of the gradient, in the direction that decreases your loss. So like here you can be like, oh, I want to head toward the center of the bowl. So you kind of head back, right? And as a result, your slope would go up a bit, and your y-intercept would also go up a bit. And then when you like take this other step, once again, your slope is increasing by a little bit, your y-intercept is increasing by a little bit. So if you were to draw a line, so if you were to draw a line, mark it there. All markers I eventually, so it's never. So yeah, I hope you can kind of see like these like super thin lines. Okay, so what that would represent is like, suppose I'm actually graphing this y equals mx plus b, right? Then like I would start with it would have very low slope and very low y-intercept. So it would kind of be like this, like a really flat line, like near the origin. Then if I take one step in gradient descent, I'm increasing the slope and increasing the y-intercept. So then this line would kind of move up a little and also get steeper. And it would kind of look like that. And then I keep taking more steps like that, and eventually I get to that theta I have, which is like my optimal solution. And then the line has like these like kind of high slope and kind of high y-intercept, so it kind of looks like this. Like, woo. Does that make sense? So even though you're wiggling these parameter values in slope and this y-intercept, like what that looks like for this point example is like your line, like the function you're learning, is like this linear function, it's changing and becoming steep. Like when you so like when you make these like little steps in this parameter space, like this like plane of like all possible parameter values, what that really looks like is your line is becoming steep and steep in this example. Okay, does that make sense so far?
Yeah, so for multi-dimensional like machine learning models, are you doing multiple gradient descent functions or is it one gradient descent function that takes in all the parameters?
It is one gradient descent function that takes all the parameters. So roughly what it looks like is like so in this example, right, you only have like one degree of freedom, like one parameter that you can learn. So your derivative is like dl divided by like d like w, where the parameter is a single scalar number. Okay. And like, oh, if I wiggle this w by like a tiny bit, and like I increase it by a tiny bit, I decrease it by a tiny bit, how does the loss change? That's what the derivative or the gradient is encoded in this example. Then when I go to this example, what I'm doing is I'm wiggling both m and both b by a tiny bit, and I'm asking how does the loss change as a result of that two-dimensional change? Because now there's two parameters. So that would be now you call it the gradient, but it's still the derivative of the loss with respect to each individual parameter. So really, there's a dl by dm, which is how the loss changes when you only wiggle the slope, and then there is a dl by dp, which is how the loss changes when you wiggle the y-axis. And you incorporate both of those numbers into your gradient descent. More questions? Oh yeah. And as for like high dimensional, when you have like way more parameters, you're still doing the same thing. You're still doing like, how does the loss change if I wiggle each individual parameter by a tiny bit? And you incorporate all of that into your gradient descent step. So what that would look like is like, if you have like 1,000 parameters, right? You would have 1,000 like individual derivatives, like derivative with respect to the 501st parameter, right? That's one number. But it's actually a vector of like, let's say 1,000 or 100 parameters. And that's what, yeah. So it's like a vector of 1,000 of these like individual derivatives.
What happens if you have like 10 billion parameters like that?
Have fun with that. That's what you're gonna do. That's what all these models are doing. They're taking the derivative with respect to like billions of parameters at a time.
Does it need to be minimized?
Yeah, so you're trying to minimize the like for the reason you take the derivative with respect to each parameter is you're trying to decrease the loss.
Like average loss over all of them, or?
You don't have it. You're just trying to change the loss if you like only modify one parameter at a time. So it's kind of an assumption you're making that like if I modify one parameter, it sort of like happens independently of this other parameter. Like you only care, like you treat it as if there's only one parameter to wiggle, but you do that for every single parameter, you just wiggle all of them once. All right, anyone else I can use, the question about it? Okay, so this is like a summary of, this is like a pseudo algorithm of what I was talking about. So you just repeat this over and over again. First, you take the derivative of the loss with respect to your parameters. It can be like 1, it can be 100 billion, like all those things, like all those examples like occur. You calculate the gradients, which is like the derivative of the loss with respect to each individual parameter. So that was like, if you go back to the previous slide. So that was like these little orange arrows here. So like this arrow right here, this is like your gradient. That is like, that is the derivative of the loss with respect to your two parameters. And like that's the result when you calculate the gradient. And then you take a step in that direction, and that's what gradient says. So you repeatedly calculate those little arrows, which are little steps in your parameter space, and then you move in that direction. And you repeat that. And hopefully, if you do that enough times, your loss will continually go down, and you'll find a nice like low position in your loss list. Okay. Any questions so far? Okay, what time is it right now? Are we on time?
5:30. You got time. Yeah.
Next slide, please. Okay, so this is what it actually looks like if you like write out all the equations. So again, we have our derivative of the loss with respect to the first parameter, our slope, and we have our derivative of the loss with respect to our y-intercept. And the idea is the gradient is just the vector containing these two numbers. So in order to calculate each individual derivative, though, what we do is we have to take the derivative with respect to the loss. So for this example, we're going to use the squared, we're going to use squared error or squared loss, just because it has a nice derivative. So the squared error is the square of the difference between your prediction and the actual answer. So we plug that in. I guess I'll write that. So it's like you have your y hat, which is your prediction, you have your guaranteed answer, and then you take the square. And that is your squared loss. And when you take the derivative of that, what that looks like is move to like your power rule, you move the 2 down here and decrease this by 1. So you get 2 times the y hat minus the y. And because of chain rule, we're trying to take the derivative with respect to the parameter. So you can break down this derivative with respect to the parameter into derivative of the loss with respect to your prediction times derivative of prediction with respect to one parameter. And like that's courtesy of chain rule from calculus. And then if you plug in like actual expressions for each of these terms, what you'll get is that thing on the right, which is 2 times the difference between prediction and ground truth times your input into the function, which for y equals m is supposed to be is just x. Does that make sense? Okay, and then you repeat that for your y-intercept. The derivative of loss with respect to your y-intercept is actually derivative with respect to your prediction times derivative of your prediction with respect to the y-intercept. You get this. Now you have your gradient. So you take a little step in your parameter space, and you have your original value or your previous value of your slope and your previous value of your y-intercept, and you just take a little step according to the derivative. So 2 things here. There's this minus sign here, and there's this alpha here. So the minus sign comes from the fact that the gradient is actually pointing uphill. So that's like a minor thing that causes confusion sometimes. The gradient points uphill. So actually, if you want to walk downhill, you have to take a negative of that. So that's why we have this minus sign here. If you did plus sign, what you would actually be doing is you'd be walking uphill and maximizing your loss. And your model would have the nonsense all the time. actually, it would probably be like, you're taking multiple choice, like, tests, and you like, you're really great, so you know all the correct answers, and then you deliberately choose the wrong answer for every question. And that's how you get the lowest possible score. Because if you guess, you would get something right on accident. So maximizing your loss is like if you try to maximize your loss, what your model will learn is actually how to get every question right and get them all wrong. Like that's probably what it would learn. Yeah. So since we want to minimize loss and make our model perform accurately, we do the minus sign, we decrease loss. The other thing is this alpha here. So the gradient is actually just a direction. Like the gradient would, like for this example here, the gradient would be like an arrow pointing like, oh, I want to go left, or I want to go right in order to decrease the loss, right? But that don't give you a direction. That doesn't tell you how far to step. Like if you were like here, right? And you're like, I want to go left so that I can decrease the loss. But if you make a giant step, you'll like end up over here. And like that won't help. Like you just skip over all of this. If you make a tiny step, then you'll like move a tiny bit down the hill, but you're still kind of like you make no progress. So the question then is how do you choose like how big a step to take? Like you have your direction, like I want to go that way. Like if I was trying to minimize the loss, like from up here down to here, like down the stairs to the ground, right? I could be like, okay, I'll take a tiny step and like kind of like scoop on the counter a bit, and like my loss won't actually go down that much. Or I could take a giant step and like end up like on that counter over there. Like those are all possibilities depending on what step size you choose. What you want is like a reasonably sized step that kind of takes you over here, but it doesn't take you all the way over there. And unfortunately, I don't think there is actually a good way to choose your step size. Like this number here, it's usually somewhere between like 0.01 and like it's probably gonna be something like 0.01 or 0.1, 2, 3, 4, 5, something like this, like 10 to the -5. Or like up to like 10 to the -2, somewhere like in that range. Like one of those things that you just kind of have to like try a bunch of different values and see what works. And there's a bunch of like other stuff like ways that like automate is like you continuously decrease your step size as you go. So like over time you make smaller and smaller steps. Or there's others that are like, oh, like your step size will like go down, and then you'll reset it to big step size, and you'll go down over time and reset it again. Like, there's all these weird ways to like change your step size according to like these weird rules and like weird patterns. But you kind of just have to try it on, as far as I know. Any questions on that? Tangible or gradients? When you break down this derivative expression right here, when you break that down into like these two like subcomponents, that's using the chain. The whole thing where you calculate your derivatives to get your final gradient vector, and you use that gradient vector to update your parameter values, that whole thing is one step of gradient descent. And you do that whole thing many times. Okay, is anyone here like hopelessly bored? Like anyone at all who's just like you're not there to hear any more of this nonsense? I want to make sure I'm not going too fast, too slow, or too easy. So now's your chance to complain.
We never actually calculate those things like I can do it.
No, you have to do it by hand. Yeah. So like usually like what people do is they have like a whole stack of paper notebooks and they write down everything by hand for every single step. And it takes them 20 time. I'm just gonna the computer does it all for you. Although I feel like yeah, people who worked on this stuff like decades ago, or like a couple of decades ago, they'll be like, back in my day, like all these nice like Python libraries, like these days, all these nice Python libraries, do it for me. Back in my day, I had to like implement programs, like all these gradients. I had to do that myself in like a horrible language, like C or something. That would like crash all the time.
Fortran.
Yeah, Fortran, whatever that is. Like I have to implement all that myself, and like now you kids, you don't know how to figure that. It like my script does it all for you. Like that's a thing some people say. But like now the libraries do it all for you, and you're mercifully free from having to do it yourself. This is it, right? Okay, so this is like just a tinier version of what I drew on the board, but maybe you can see it better. So like you have some like value of your parameter, which I guess is your slope, right? And then you want to decrease the loss as a function of your slope. So you just walk down the slope and you hopefully get to the bottom here. So this one on the left is nice. It's just like a smooth bowl. So like if you keep walking, you'll easily hit the center of the bowl. But sometimes you have a horrible loss density like this monstrosity. And you could, if you start like anywhere up here, like you could get stuck up here. And like the loss is actually like not that good up there. But like unless you like have some tricks up your sleeve, you'll just get stuck there. And same with like on the right hand side, like if you do gradient descent, like starting like all the way up there, then you'll kind of like hit this right here and get stuff. And it'll be hard to find this global minimum, which is the best possible solution, like the best possible parameter value. Okay, so now we're gonna layer on like a little technicality. So what I was describing to you so far is like normal gradient descent, sometimes called batch gradient descent, which is when you take the derivative with respect to your parameter, you do that for every single training example you have, you take the average. So the idea there is it's how to wiggle your parameter values so that your average loss across all your training data goes down the most. But that's across all your training data. It's like a single step that will improve your performance on your training data the most. But that's expensive because you have to calculate the gradient with respect to every single training example. And sometimes like your data set is like, it's like a million examples. So if you want to take one step and do the full batch gradient descent, you have to calculate your gradient like 1 million times, which is horrible, like it's super slow. So what people do in practice is they take a subset of the data. So like if you had like a training set with 1 million examples, what they would do is they would take only 100 examples. And they would calculate the gradients for only those 100 examples. And they would average that. So like 100 gradients divided by 100. Like you have a gradient that gradient is not perfectly accurate because you only use 100 examples. There's like 999,900 other examples that would ignore. What people do is they'll just use this like very approximate gradient that only incorporated 100 training examples for the calculation. They'll use that instead because it's faster. That's it. It is a less accurate gradient. Like when you like move your parameter space, it's not actually the best direction to move, but it's just so much faster that people do in practice because let them take more steps to it. Like sometimes people say, oh, it's like a drummer walking, like versus like super careful person one. So like the super careful person who's like the full batch gradient descent person, they'll be like they will carefully calculate everything. They'll be like, what's the wind direction, what's the humidity, what's the temperature, like what kind of like ground am I like? Is it gravel? Is it sand? Is it like rock? They'll be like, what did I eat yesterday? Like, what's my heart so like rating today? Like they'll take all that information into account and then take a tiny step and be like, that's all I can say. And then they'll do the whole conversion super slow. You do stochastic or mini batch gradient descent, you're doing this, you're being a lot more reckless. You're going like you're moving past some gradient things. And you're just like you're not being perfectly accurate. You're kind of choosing like kind of wonky directions, but also moving super fast. Even if I like all the way over here, oh my god, I'm drunk as hell, I can't see anything. Eventually you'll just like stumble onto a low loss area. Like you didn't think, you just kind of like hang around, but it worked. You got to the low loss area. So that's stochastic gradient descent any time. So stochastic is usually when you use one example, the derivative with respect to a single example. So that would be like with the object detection example, I have like one single image of the dog, and you would be like, how do I wiggle my model parameters so that like the box I draw is as close to the ground truth box as possible? But only thinking about that one image. There's like a bunch of other dog images that you can ignore, right? But because you only care about that one dog image, it's a super fast calculation, so you can take a bunch of steps. So that's stochastic gradient descent, where you use one example. Mini batch gradient descent, you use like some number, which you kind of have to choose yourself. Usually it's a power of 2, like 16, 32, 64, 128. And you use that, even if the training set is gigantic and millions of examples, you just use like a tiny subset. And the great thing is, it's way faster and actually gets you to a good optimum, like in the end. And even if each individual step is not that great, it like overall it actually works out really well. And there's also some stuff about how like this actually like helps you because like you're not. Okay, actually, we're gonna ignore that part because it's kind of like an extra caveat. Like the thing to keep in mind is just that like when you use a subset of the data to calculate the gradient at every step, it's way faster and it works pretty much as well as using the whole thing. So it's good enough. Okay, so let's go over what has been described so far. So we have many problems which are hard to write an explicit program for. So we turn to machine learning because we give a model a bunch of data and we tell the model, please figure out like your own parameter values so that like you do whatever task I want you to like on this data. You do a lot. So the question then is, how do I actually pick these parameter values for my model? And the answer that people have converged on is use gradient descent, train your model. And that training in the end is always about minimizing the loss of. So the visual intuition again is you have your loss landscape, you walk around the loss landscape, trying to find the lowest point in your loss landscape. And the way you do the walk is you gradient descent. So at every point, look around you, 360 degrees. Like I can say that I can't actually visualize. No one can visualize. So you like look all around you and say, which direction will take me downhill? You walk in that direction. You do it again, which direction will take you downhill? Walk again. And eventually, you do that enough times, your loss will go down a lot, and you will get a good system. And the other way to like think of this, like it's a ball rolling down the landscape. Like it's the same thing. Like gravity will try to pull you down, so inevitably you'll just follow whichever direction takes you down. Okay, so that was an introduction to machine learning as a general concept. This idea of choosing a model of parameters and then choosing values for those parameters to minimize the loss function. Like that's machine learning in general. And now we're going to talk about a specific model. And we're going to be more explicit about what the parameters are, what they look like. So a perceptron is like the most basic form of neural network. A neural network in general looks something like this. So it's like it's got a bunch of nodes, it's got a bunch of like edges between these nodes. The high level overview is you take your input, you pass it into the input layer, and then those values get passed from left to right. So you pass it to the first layer, the second layer, the third layer, fourth layer, and then finally to the output layer. And then whatever came out of the output layer, that's your model's prediction. So going back to our machine learning framework, what we want is we want our model to take in some input, which is usually a vector of numbers, and then pass it through the network, through this neural network model, and output like another vector. And hopefully this prediction vector is really close to our ground truth label. And for vectors, a lot of the time we'll be using squared error loss, which is just like the square of the difference between each element in the vector, like all the way down the list of numbers. The model in our case is this neural network, and it has, you can group the parameters of the model into two like high-level groups, which are the weights and the biases. And we'll go into that one later. Okay. So one thing to keep in mind before we like start going into the exact details is this high-level overview is a little deceptive. It kind of looks like each node kind of looks like you're just taking, like you're doing one operation to get from like this layer to this layer. Like you can actually kind of slice each node into like two halves. So just keep that in mind, like earlier. Okay, so this is what one layer looks like. So you have your input vector as which is like a list of numbers, and then you have a weights matrix, which is one type of learnable parameter that you have. It's a matrix of numbers. Each number is one parameter. You also have your biases vector, again, learnable parameters. You have your activation function, and you have your output vector, which gets passed on to the next layer. So the idea is you start with your vector, xk, this is your input. And then you do a matrix multiplication with your weights matrix. And that gives you, this together gives you one vector. Then you add this vector with the biases vector to get another vector of the same length as before. Then you pass that vector to this mysterious activation function, which we'll talk about later. And that outputs yet another vector, which is this xk plus 1. So this xk plus 1, the k plus 1 means like it is the output of layer k, but also the input to the next layer, layer number k plus 1. So a few things to keep in mind is that aside from this activation function here, everything actually follows like a very strong, like linear structure, like a very linear outline, very linear algebraic thing, where like you have your new matrix multiplications, you add vectors, like everything, you can almost think of it as like a y equals mx plus b, like all over it, except the n, which was the slope, we replace it with this weights matrix, and the y-intercept, you replace it with this bias vector. Yeah, all right, thanks. Okay, so we're gonna walk through a painstaking example here. So before we do that, any questions? All right, if you have like no idea what question.
Yeah, what are the weights and biases?
So the weights and biases are your learnable parameters. So we're gonna like do an example right now, but at a high level, your weights are a matrix of learnable parameters, and your biases are vectors of learnable parameters. So like, using a very Minecraftian, Minecraft is a good way to like visualize this, because everything is like nice rectangular parts. So your weights matrix is like this, it's literally just a matrix of numbers, right?
Ow.
One number. You have a whole matrix of these. And your bias vector is like a special case. So like it's just one column, but like one row. Yeah, something like that. Okay. And the thing is like both of these are learnable parameters. Every single number, every single value in both your weights matrix and your bias vector, they all get learned by a gradient descent. Like you calculate the derivative of the loss with respect to every single number, and you wiggle every single number at every step of gradient descent. Okay, before we get started on this example, I'm going to check it. Is anyone like hopelessly lost by what I'm like? Because if you are, then I'll like read it again. All right. Either they're super confused or they're just big brain. I know what you're doing, which is great. I don't have to do my job anymore. All right. Okay. So what we're going to do now is we're going to walk through like one example of just like walking through every single component of like a simple network, just so like you have like a very like low level understanding of all the components, which will help you in the future. So we're gonna pass an input into the first layer of the network and see what comes out. So in this case, our input is a two-dimensional vector. It just has two numbers, x1 and x2. And like that's your input. Then we want to pass it through the first layer of our network. So what that roughly comes out to is you do a matrix multiplication with your first weights matrix, then you add that result with your first bias vector, and then you pass that sum through your activation function. And what comes out at the other end will be your x1 vector, which will be a vector of 3 numbers long that will be passed into layer number 2. So we're going to walk through the individual steps of doing that now. Am I taking too long? Okay. Speed. All right. So a matrix multiplication is actually a bunch of dot products. So like suppose okay, I'm gonna kill this bias vector for now. We'll come back later to want to. So like okay. Okay, all right. Okay, so now this like smaller version is accurate with the slides. So what we're doing here is first we do a matrix multiplication with our weights inputs. So we have our input, which is the x1 and x2. Like it's got two numbers in the vector. This is our input. Then we do a matrix multiplication with our weights bias, with our weights matrix. And then once we have this matrix multiplication result, which will end up being a vector of three numbers, we add that vector with this bias vector. And this sum of the matrix multiplication with this bias vector will also be a vector with three numbers. And it'll look like this. Then we take this vector of three numbers and we pass it through our activation function. So the activation function actually maps from like number to number. So it'll be like activation function of like this like first number, the second number, and the third number. This vector of three numbers, right? But what you're actually doing is you're actually doing activation of just the first number, activation of just the second number, activation of just the third number. And like this is your output vector. You're actually applying the activation function to each individual number in your vector. But we just write it, like people just write it like function of a vector because it's just faster to write it. And the thing is, this matrix multiplication, you can actually also think of it as being a bunch of dot products. So like this x1 right here, this red number right here, right? That's actually the dot product between this first row right here and your input. That dot product is a number. You take that number and you add the red bias number to it. And that single number is your x1. And then you take activation function of this number. And that'll be your first like output. Then you do dot product of the middle row with your input vector, and you add this middle bias number here. And that'll also output a second number. And you take that second number, you put it through your activation function, and you get the second number right here. And you do that for everything. So you can think of it as like one big matrix multiplication and one big vector addition. Or you can also think of it as like every single number in this long vector is actually a dot product plus you add a bias. But the higher level version is to think of it in terms of matrix multiplications and vector additions. And this is like what it looks like in the like neural network line diagram. Like there were a bunch of like edges between these nodes in the first diagram. So when we think of it in terms of dot products, then you can kind of break it down into smaller subcomponents. And then only the edges that go from the input into your first node here, only those edges are relevant into your first dot product. And also, the first bias number, only that one's relevant when you're trying to get your first number in your output. And then when you want to get the second number here, then you take dot product of your input vector with only these two edges, two edges, and you only add your second bias. Yeah, so that's the green. So if you're confused, then later you can go through the slides, and everything's been color coded, so it should be relatively straightforward to just like trace everything out. Okay. Yeah, and this is like the high level overview. you have your input vector, you do a matrix multiplication with your weight matrix, then you add your bias vector, and that's your output. And then you feed this through an activation function. And then whatever comes out of the activation function, you pass that on to your next layer. And it's honestly just that. Like you do this with the activation function, you just do that like layer 1, layer 2, layer 3, layer 4, layer 5, and like 100 layers later. Like that's the output of your neural network. Okay, any questions? Since I'm sure there are questions. There's no way I explained it well enough to where there's an amount of questions. Questions?
I
think they'll get sent out on the resume at some point.
We know how many layers we know that we get a
Good question. Ask that question. Why did you have to ask that question? It's an annual question. Nothing. So the thing is, like, there's no formula for taking the number of things. Like, you just kind of have to try a bunch. And there's all these weird unintuitive phenomena. Like, and one of the intuitions is, if I have a neural network, with like layer 1, layer 2, layer 3, and like so on, right? Wait, can everyone see the diagram? Okay, like if I pass my input into this first layer and then pass it through the subsequent layers, then what happens? Then like you would think, oh, like I can process my input to this first layer. Then my second layer can process that one. Then my third layer can process that one. And like with more and more layers, you can like do more and more process. You can like come up with like more and more complicated like operations to run on your input, essentially. But people have found that if you put too many layers, it actually causes problems and reduces the performance. Like sometimes having fewer layers is actually better. But I don't know of any like hard and fast rules to like determine the exact number of layers. It's just a thing that people like have to try a bunch of different like configurations and like layer numbers and see what happens. But some general rules are that the more layers you have, the more complicated functions you can represent with your network, as a general rule. And the other rule is that usually if you have a fixed number of parameters, it's better to have narrow layers and lots of them than to have a few layers that are extremely wide. So it's better to have like a lot of really thin layers than it is to have like one like really wide layer. So like instead of making like this matrix like super tall, it's actually better to have a shorter matrix and just have lots of layers. Okay. Any other questions?
So in this example, there are 3 layers inside the neural network.
No, this, are you talking about like this like generic?
Yeah, so like red, green, and blue.
No, the whole thing, this whole thing is one layer.
One layer.
Yeah, and sorry. Yeah, so like when I go from this input vector to this like vector of 3 numbers, that's the operation of one layer. You just pass it from input to output of the first layer. And another like way to think about it is like each vertical column of like these blue like nodes, that's one layer. So like I start with my input and I pass it through like all these matrices. This actually just shows the matrix multiplication. I pass it through the matrix multiplication and my activation function. And now you're at your first layer. Then you pass it through to your second layer, your third layer, fourth layer, and that one's your output, so you're done. The color coding was to show like what happens if you're only focusing on like one individual like blue circle, one node in one layer.
So that one layer has 3 nodes, so you have to pass it to each node.
Yeah. And if you want to think about it in like if you want to think about it on one level higher than individual nodes, then you can think about it as like matrix multiplication. And like that one matrix multiplication incorporates like all of these edges right here, all of them. Okay, any other questions?
What do you mean by edges?
So edges here is like in like a strictly like graph sense, like you have like your two vertices and like a line between them with an edge. So like if you think about it in terms of like matrix multiplication and all that, then actually one edge here is one number inside a matrix. And so like if this is my input vector, right? Yeah, I'll make it longer for illustrative purposes. If this is my input vector of 5 numbers, right? And like I have a layer that goes to like 2, right? Like there would be like a bunch of edges going between these nodes, but if I'm only like one edge here is one node, right? And then if I incorporate all these edges going from input to one node in the output, like these 5 edges represent 5 numbers, and those 5 numbers represent the dot products. I represent one global matrix, so it would be something like so like this is your input vector, right? You do a matrix multiplication to get out a vector with 2 numbers, right? Which like corresponds to these 2 nodes right here. But like these 5 edges right here that kind of converge into one node, that corresponds to the top row right here. Like when you like when you do this dot product here with the first row in your input, that is the same thing as like the dot product with this input vector and like these 5 edges. And that gets passed to this node. And then if I add these 5 edges, like going down to the bottom node right here, that's the dot product. Okay. Any questions?
Oh, the data you use in your output, right? The output matrix.
Wait, which one?
The data next to that.
This one?
Yeah, that's the output matrix.
This is the weights matrix. Yeah, and this vector right here, which is like this one, is the input.
Yeah.
And I'm not drawing the bias vector, since like people in practice they just kind of ignore it, like, oh, bias vector, it doesn't exist. We're never going to draw any for diagrams. It kind of what's under here. Like it's still there. We're just not drawing it because we're lazy. Or I'm lazy. I don't know about you guys. Maybe you guys will draw the bias vector whenever you have to draw. Oh yeah, so this just shows the individual dot products. And that's the high level overview. Okay, so next we're gonna go to part 4, which is activation and loss function. Wait, I'll do a little bit. So I kept glossing over the activation function. It was like, you do this, you add your bias, and then now you have your vector, and you pass it through an activation function, which we're not gonna talk about, because he's gonna talk about it. Now we're gonna talk about this one. Yeah, and before we get to that, any final questions about like the stuff we've gone over so far?
Yeah, so I think there was a question like this already, but are the weights and biases in the determine already?
So usually what you'll do is like the weights matrix and the bias vector for every way, what you'll do is we'll fill them with random numbers. And then using gradient descent, you'll gradually learn each number until it gets to, until like all the numbers get to values that give you a good solution. That make sense? Any other questions? Have fun, guys. Totally not let people do like a small amount of.
All right, thanks, Malcolm, for his amazing presentation. Just before we get into activation and loss functions, can everyone go back to I don't know if it's in here. No. Here. So apparently, I think there was some problem with check-in or something. So if you guys like try checking in again with this link, I think it's a Google form.
We'll give you points for merge if you check in at
Yeah,
positive events.
exactly.
what can you buy with it? You get like water, you get water bottles? You can get like stickers,
Stickers, pens, mechanical pencils, oh, I guess the things you can get with points are, get stickers, pens, pencils, keychains, t-shirts in black and white, as well as hoodies, as well as sweaters. Yeah. All of them.
Really know a lot about this.
Yeah, I redeemed a lot of points last year, but I remember it was out of the this one.
He's your role model. I don't know what's that.
Snazzy hoodie, guys. I have like a t-shirt, a hoodie, and a mechanical pencils. I really like it. There's nobody can to explain anything about loss functions.
Is everyone ready? Everyone got the check-in codes? Perfect. There you go. All right, let's start with activation and loss functions. Malcolm actually went through part of it, because we're running on time. So I'll go through this part fast. And if you guys have any questions, ask any of our board after the meeting, after this workshop. All right. Let's first consider an example of a multi-layer perceptron, like this thing. Remember that right now I use perceptron. We defined that the perceptron function is x prime equal to the activation function times the weight matrix times x plus b. Yeah, that's from the last section. So a question is, what would be the output of, hey, this node in red, this perceptron in red? You guys can like discuss among yourself very fast. Which of the A, B, C, D would be the output of A? Oh yeah, and if you know the answer, like raise your hand. Pretty fast. All right. Are there any volunteers? Yeah. Is it B? Does everyone agree with B? Yeah. Yes, you're right. It is B. That's correct. The reason why the other ones are wrong, well, it's pretty obvious. But the first one is like we're finding XA and then we pass an XA, so that like makes no sense. And C, it's like it's missing the activation function. And D, it is true, but it's for this perceptron at C. Cool. However, although like C without the activation function, why do we really need the activation function anyways? Like, why not just like have C instead of having an activation function surrounding this function? So to answer this question, let's try to solve for this the total output y given x1 and x2. So starting from all the way from the beginning. And so if we don't have the activation function, then first we can find the output of perceptron A, perceptron B, and then we know the perceptron C in terms of the outputs of perceptron A and perceptron B. And yeah, so for the first one, that is the equation without activation function for perceptron A. The second one is for B, and the third one is for C. Are there any questions? Okay, let's delve into the bit of math. So we want to find y in terms of x1 and x2. And we have that y equal to this xa, xb function. And let's just try to like substitute the xa function and xb function into it so we can solve for x1 and x2. Yeah, so that would be the extended form. We can distribute it. It will look like this. You look closely at it. And we can regroup it. So after we group it again, we end up with this x1, this x2, and then a lot of like bias and stuff there. All right, so since the weights and biases are all constants during computation, so like before we go through gradient descent and stuff, they're all constants. So if we see that these are constants, and these are constants, and these are also constants, what we can do is we just define a different constant that represents that. So we get that. We have a constant weight multiplied by x1, a weight multiplied by x2, plus a bias. Yeah. So what can we say about this? Any volunteers? Yes.
So it's basically you just really think about it. It's not like just one layer and just straight up to the output.
Yes. Basically, with that, we end up still with a linear regression function of x1 and x2. This is basically just one equation of a perceptron. So we can like literally represent everything with just one perceptron. And so in fact, the linear combination of linear regression is just a trilinear regression that is still a linear function, or still a linear regression.
Say that 10 times fast.
Hmm?
Say that 10 times fast.
Say that 10 times fast.
It's like a linear combination stuff.
Okay, yeah, so that's the activation function. Now we like know if we don't have the activation function, everything just really becomes like one linear equation. And so by introducing a non-linear activation function, G, the output x, x prime can be non-linear. So this is without it. This is, well, it can solve some problems with like, obviously like linear boundaries and so, but like, want to solve some more complicated problems. And this is what non-linear means. I haven't talked about what activation functions are, but these are some like widely used ones, sigmoid, time edge, ReLU, DT ReLU, maxL, and ELU. So these are basically like activation functions that we put on the outside of our like output vector. And then yeah, so these will like make some nonlinear behaviors to our boundaries. Yeah. So basically activation function creates like a decision boundary or like a nonlinear effect that would change the linear regression to like a more of a different like boundary line. And so the combination of like many nonlinear equations can make very interesting boundaries. Yes, question.
So when you're like with each of the bonds in this new map, and then one was exactly with another, all of these combinations. Like W1 X1, W2 X2, W3 X1, W4 X2. Each node.
So wait, wait, can you repeat your question again? Sorry.
The first diagram showed that I had 3 layers of zeros. Like
Yeah.
no, use the first diagram we had
Like this?
before.
Before this.
The
Okay.
so on each of these, the function you
Yeah, so each of these nodes are perceptrons.
Yeah.
And so basically inside this, I think Malcolm said you can split into like 2 parts, but basically like the second part is the activation function. It like calculates the activation, it passes the things that we found from the matrix multiplication, and then we pass that vector, the output vector, through an activation function, and then we still get it's like a 1-1 matching, and then we get like a nonlinear or like form of the vector, and then we pass that on to the next layer. Yes.
So each edge represents
like the input going through the activation function?
No. So the activation function is in this node. Yeah. So these edges like represents this is the output from this perceptron, and it goes into this perceptron as the input.
And then after it's put through the activation function, it's then brought to the next perception.
Yes. It's everything is done in these perceptrons. Any more questions? Yes. Oh, that's a good question. Let's see. Yes, so similar to what is it? How many layers we go in a neural network? This thing is more like a designer choice or something. So basically it's like trial and error. For some problems, like sigmoid works better. For some problems, ReLU works better. I guess in a common consensus that ReLU usually works the best. But for some scenarios, Panage or sigmoid also works pretty well. Okay, we can try to visualize like what is it like with or without activation functions. A very good site to play with neural networks is called the TensorFlow Playground. If you can go to this link, it's acmurl.com/TensorFlow-playground. You can try to play with different activation functions and data set. Don't worry about like how the network is training. We'll go over that in the next workshop about like backpropagation and stuff. Okay. Is everyone here? Cool. We can try to play with different, let's go with regression because that's the problem that we were going for. And we can go for like, for example, this one. Let's just keep the neural network as how it was. We can change the activation function to linear. And then if you try running it, like basically the output boundary is just still linear. If I can just show discrete output. Yeah, so the boundary is still linear. This is not what we want, but for this question though, it's pretty good because we can just separate everything by linear boundary. But if we want to look at other data, for example, this one, yeah, the data set in this is you require like nonlinear boundaries to work for. So now if we run without activation function, they said linear as activation function, but that basically means there's no activation function. And yeah, it still makes like a linear boundary, but it doesn't really classify the points very well. You see, this part is orange, but it's in the blue area classified as. So if we try to play with other activation functions, for example, ReLU, you see that like the boundary shifts, and then it looks like it classifies it better. So now I think that's a pretty good accuracy. Yeah. So that's like the effect of adding activation layer at each of the neurons. That this creates like a nonlinear boundary effects to our model. And what about this good side that is this TensorFlow Playground that is good? You can like click on these neurons and see like what boundaries they make or something. Yeah. But that would be all I would say about the activation functions. Let's go back to the slides. Does the visualization make sense? Does it like help you understand more about why we want activation functions? Okay. Okay, loss functions. Yeah, I think Malcolm already went over part like many part of this. Basically, we want to have a metric to evaluate the output of our neural network. So the output of our predicted output, and we can update it. We can compare it with the ground truth, and then update our weights and biases. For example, in the regression problem that we were just going over, we can use this called mean square error, which is basically taking the difference between our ground truth and prediction, and then squaring it, and then having 1/n, which is like normalizing it, and then that will be the error. So if our prediction is closer to the ground truth, this part will go more to 0, and then the loss will be like more to 0 as well. But if our prediction and ground truth is like pretty large apart, then our loss will be big. And so this will give like a metric for the neural network for our model to know how to like train toward the optimal values for the weights and biases. There are a lot of loss functions. Because there's a lot of problems that you can solve using neural networks. Of course, there's gonna be a lot of different losses. Depending on the problem, you can have different loss functions to use. And often you like to experiment with different loss functions to see which one that works best for your model. Are there any questions? Yes.
Can we say a bit more about the mean square error?
The mean square error, okay. So the mean square error,
So does that give us which like a value?
yes, it does.
And how can we use that value to see whether our prediction is accurate?
Oh, yeah, so basically, in this case, the n is the number of, or we can say the batch that we pass into the neural network, and we will get like, let's say, let me phrase this better. We have n ground truths to predict. And then, so we will get n predictions. And we want to compare the corresponding predictions. For example, let's just look at one prediction and ground truth. If we take a difference between a ground truth and a prediction, we'll know like how far apart they are, right? And we take the square because sometimes it's negative. Because sometimes, let's say the ground truth is smaller than the prediction, then we'll go negative. But we want to have it have a matrix that the larger the loss, then the worse the ground truth and the prediction are apart.
So the number should be a small amount.
We want to get the error to be as small as possible. Closer to 0. Yeah, so you can see this when the ground truth is equal to the prediction, which is what we always wanted. Then this part goes to 0, and our loss goes to 0, and then we're all happy.
Would that consider overfitting if our mean square error is too small?
If mean square error is too small, we can't ask overfitting. It is possible. Yeah. So let's say our training data set, we got a very good, we get our loss all the way down to 0. But there's also maybe our test data set is different from our training data set, and that the test data set have some distribution shift, which is it has more of a critical data set part that our model couldn't really solve. And I would say that's a problem with training. So if we train too much, the neural network will work perfectly with the training data. It's like memorizing what training data is and just giving the answer. But then if we pass something that is different, like a testing set, and it is possible that the more we train on our training set, the worse it will get for the test set, because we're just memorizing the training set. And there are some loss function that reduces that. It's there's one that uses I don't know if it's here. But if you want, you can look into something called regularization that does that tries to prevent overfitting. Yes. Yes, so it depends on the problem that we have. For example, for a regression problem where we're trying to predict a number, like to get the ground truth number to match up, the prediction number to match up closely with the ground truth number, then we can use like some of these regression losses. And if we have some problems like classification where we want to like classify if this image is a dog or a cat, then we can use some like classification losses. And there's also other ones that I'm not quite sure what is ranking loss and contrastive losses, but for reinforcement learning, which is like a different field of AI, there's also losses for that. So it really depends on the problem you're working on, and just like playing with these errors and see how well they work. Any more questions? Do you have any questions like regarding loss function or activation function that you have like come up later? You can ask our staff, our board, about it like after this workshop. Cool. So yeah, next part will be training on MSDS that I'll pass it to Sandra.
All right. Hello, everybody. My voice is still recovering, so yeah, you're gonna have to deal with this for our next 22 minutes. Attached is a link for a collab that we have prepared for this workshop. It has resources on gradient descent, a bunch of other cool stuff. The main thing I'd like to point you guys to is actually the bottom of the workshop, or the bottom of the collab, which considers like training on an actual data set. In this case, is that bright enough? You guys like kind of see it on the board? Oh, all right, cool. So I guess we've been learning a lot about what machine learning is, sort of the math behind it, as well as some of the design principles. However, we've never actually like done a problem, right? And this was, at least in the beginnings of ML, this was a problem that researchers, or at least individuals, try to solve. Let me ask you a question. How many guys have sent an envelope in like the public mail, like in the post office? Okay. Do you guys have to write a zip code on there? So in that case, right, like, let's say back in the day, right? Back in the day before cameras and cool stuff, right? A human has to read the numbers on that envelope and send it to the accurate zip code, right? Or send it to the accurate address, right? Now, with so many envelopes, right, routing becomes difficult, as well as just processing that much amount of mail, right? So a couple of researchers were tasked by the US Post Office to come up with a system that predicts what numbers are there on an envelope, or what zip code is being represented by. And they provided a data set of 60,000 images of handwritten numbers. This is what we classify as MNIST. I actually don't remember what it stands for, but that's the principle behind it. There's these researchers were provided 60,000 individual images that were 28 by 28 pixels, and each one of them had a distinct number, and each one of them were labeled. So looks like we're using a couple libraries here, yada, yada, yada. These are some random images. So let me zoom in real quick. So these, I swear, I'm joining in like 18 minutes before the workshop ends. But so these are some random images provided by the US Post Office. And you can see like some of them look pretty close to like the numbers, right? Like the first one looks like a 9, right? Like the one right below that looks like a 0. Then maybe like, what's a pretty good one? I guess like the 6th one in the first row looks like a 7, right? But some of them are a bit ambiguous, right? Like, let's take a look at maybe the 5th one on the last row, and then I guess the one right next to it, right? It could look like a 6, right? Like that 5, because like its loop is almost closed, but it could also be a 6, right? And so it's at least difficult for the machine learning model to classify like whether or not like this is a 5 or this is a 6, right? It's a difficult decision. And as we've learned, right, we're essentially we have weights and biases that dictate, that the ML model uses to dictate whether or not it thinks it's a 5 or it thinks it's a 6. So you can think about it as a problem. So let me just refer to one I wrote earlier. So I mentioned, each one of these images is 28 by 28 pixels, right? So you can convert these into what we call as a vector, which is essentially just a list of numbers in one B. What's really useful for us is we can actually convert this into a vector that's 28 times 28 numbers long, right? So, yes, what's 28 times 28? Well, let's do that math there, right? Okay, the answer is 784. We're essentially creating a vector that's in 784 dimensionality, and we're having an output with 10 layers, basically. We're trying to predict whether or not these numbers match sort of the pixels of the expected numbers between 0 through 9, right? So, wait a minute. How many nodes is our output layer going to be? What is it? 9 frequency? I said 0 each. But yeah, I saw your hand. I did not forget about you. So shout out this. So yeah, our output layer is going to be 10 nodes long, right? And essentially, we're going to figure out sort of the maximum value amongst our output layer, right? And the maximum value sort of corresponds to the maximum similarity of the input provided versus what number it predicts, right? So usually, this should work out, right? Like, we have a number that's like the most similar to our reference number. That should be the number predicted. So, in this case, like, we're doing like a basic sort of computer vision idea or computer vision project. We're given sort of data formatted in tuples. Tuples are sort of just, imagine like coordinate pairs like X, Y, any two, like, any set of elements that are like 2 components long, we call that a tuple, right? So essentially, we're given images, which you can represent as vectors, and then we're given an expected label for each of them. So, as I mentioned earlier, MNIST gave us 60,000, MNIST consists of 60,000 images, and the length of each image is the tuple. So, again, this is sort of an example of what an image would look like, right? You have exactly 28 pixels in each direction. This looks like a 5. I don't even think this is like a number. It's a 5. The dimensions, at least, indicated by coordinate states, 28 by 28. The one is sort of indicating sort of whether it's on 3-dimensionality or not. What do you think the image max and image mean values would be? Yes. Well, we already committed. Right. I'll wait for another. Yes. Oh, good guess. Yes. The value of the pixel itself. Because luckily enough, we don't have to deal with colors. That's not a problem for us right now. It's a problem for us later. But yeah, so our image consists of black and white. So we can essentially have a binary value for each pixel, whether it's 1, whether it's 0. I think 1 is white, 0 is black. Don't correct me on that, but it would just be, the converse if there's the other scenario. Let's make a perceptron. So if you guys remember what a perceptron is, you can also look at the side of the class, after the workshop, it's not a lecture. Essentially, we're going to create a perceptron, which is essentially a single neuron or node, right? That contains some sort of weights and biases. That takes in an input vector of, in this case, 784 dimensional. We have an output layer, or in this case, the number of classes, right? You see the number of classes right here? That's going to be 10. The number of pixels is 784, and we're going to create a perceptron that consists of this. We're going to have like sort of an normal initial layer. We're going to try and test this out, see whether it works or not. So we essentially get what we call as a tensor, very classy word for a matrix that we use in ML. And essentially now we're going to train our model, right? We're not going to deal with sort of cross validation, any other fancy terms we dealt with in ML, interactive with that. But we're just going to have a batch size of 1. We'll use a bigger batch size next time. Data order, don't worry about it. LR stands for learning rate. So essentially how fast or how slow we want our models to learn. And the number of epochs. So let's say, like, what's a good way to phrase an epoch? the number of times we pass over our data training, we can consider as an epoch. And so sometimes the more epochs, the better, sometimes it's less. Once again, AI and ML is always dealing with design choices. Epochs could be one of them, especially with problems of overfitting and performance. You always have to keep that into consideration. So in this case, we define epochs. We'll dictate our perceptron to be the input layer being the number of pixels, the output layer being the number of classes, and we'll say it requires video. Sure. So in this case, what I mentioned earlier, right? You guys remember the NumPy workshop 2 weeks ago? I told you guys about Latin. So that's what we're doing, right? We're essentially compressing our image, which is 28 by 28, to a 1D input vector. So I just not know how to say but again, our method standard is based on Angular. So we specify a flattening function as well as a sigmoid function, which sort of switches our range to 0 and 1. So this is sort of going to be our activation function. And since we're dealing with classification problem, like classifying an image into what are 10 classes, you can essentially create a binary cross-entropy loss, right? In this case, we'll be inputting our probabilities for all our predictions as well as using the labels. And our output is a singular loss value for running entropy. From there, do a bunch of math that we already discussed. I'm too lazy to discuss right now. And then we get the sum, we get essentially our loss over a given dash. Now, we iterate over all our epochs. We calculate the number of images that we got correct. And then you have an activation function for each sort of layer, depending on the number of classes. We calculate the loss using our predefined function, binary cross entropy. And then we perform what we discussed like an hour today. 80%, right? We're essentially traveling to the region with the least amount of loss, right? We want to minimize the difference between what our predictions are versus what the actual ground truth is, right? That's what it dictates what the most accurate performance of the model is going to be. And so we calculate the gradient for each given input, and we sort of travel to the point where we minimize our loss. Once we do that, we don't want to sort of conflate our problem by using past gradients. So we zero out our gradients before we move to our next iteration. And then finally, for each given epoch, we can sort of gather our metrics. So we get the number of images that we got correct versus the total length of our data. You can see we sort of improved quite well, actually. We went from 87.25% correct. So that's a loss of like 12%. It's not great, but it's decent enough. But what you notice is that as the number of epochs increased, our accuracy also increased. We went from 87.25, we ended at 90.643. Sorry about that, guys. Finally, we can sort of test our model using sort of this make prediction. It's essentially inputting, an image into our model and finding which sort of output node has the maximum value or the maximum scalarity, right? So this is essentially just making a prediction using the math-based model that we just created, and we're finding the maximum node in our output. There's the maximum output vector for each node in our output there. Now, another cool visualization you can do. This is not going to work. Hopefully, it's going to work. Okay, it's some weird code output. What we can do is actually generalize our weights and biases. The more of the weights of our output there, right? Generally, what the model expects is this shape. This shape sort of corresponds to what a zero should look like. We have some gray regions from the models that we use. But you see there's a very distinctive shape of like a circle or oblong shape, and then like dark instead, right? That looks like a zero to me. I'm guessing that does that look like a zero to you guys? So similarly, we can generalize it for 1. That looks kind of confusing, but like, the model sort of gets it. 2, 3, yada, yada, yada. And as you continue down, the model sort of has, as it trains, it has certain expectations of what a digit should look like. And so when you pass in test data, you're able to assess whether or not these weights are actually corresponding to what you should actually see in this training data. So what's interesting is sometimes in future ML problems, you actually split your data into 3 sets. You have a training data, a validation data set, as well as a test data set. I guess I'll touch on it briefly. We'll also cover this in future workshops. Your model initially learns, right, on a training data set, right? You're just giving it an initial pass through of data so that your model can, analyze sort of trends that it sees, as well as make, some initial predictions, right? While you're training, like, if your model is getting stuff wrong, you don't want it to get stuff wrong for like the next 2 hours while they train, right? Especially when you're dealing with more complex data sets. So you have something called a validation set that sort of assesses the performance of training while the model trains, right? So from there, you can do this thing called hyperparameter tuning. It's a very fancy word for fiddling around and tweaking some values here and there, so that your model can actually. It's also the bane of every ML person's existence, because hyperparameter tuning is a nightmare, but that's a problem. In any case, once you sort of assess the performance of training on your validation set, you can now run your model on the test. Because your model has essentially finished learning. It's finished analyzing all the trends that it's seen. You sort of make sure it sort of makes sense, the performance. And now you're actually running on a different, entirely different set of the data that you were providing. If your model performs well enough on that, depends on the problem, depends on how much error you want to see, your model sort of working. In this example, we haven't used any libraries. We've used some libraries, but most of the math and most of the calculations were done by ourselves, which is really cool. Most of the time, you will be using libraries like PyTorch, TensorFlow, maybe OpenCV. Sometimes you can use NumPy, SciPy, Sklearn. There's a lot of tools at your disposal, but most of these calculate or do sort of the math behind this. You might be asking, like, why is my Slack? I need to mute my Slack notifications. Thanks, guys. What? Hold on. Cool. All right. You might be asking, like, why do you care about sort of the reasoning or math behind ML? I think it's often a very glossed over topic, because without understanding the principles behind ML, you sort of be lost in the sense of what decisions can you make to improve the performance of your model, right? Sometimes blindly fiddling might work, but knowing sort of the purpose and the intentfulness of having different values actually expedites the process of improving your performance a lot. So this is one guided example of how we use ML in context and how we just used it in the past. And now we'll be learning more advanced methods of ML in the future. But with that, I think that was all for this lesson. Jackie, you want to come up and give a couple words? But yeah, thanks, guys.
So much for attending AI School 2. So our next workshop is going to be 6 to 8 p.m. in room 2315, so the same room as the first workshop. We need to make sure to check in at second school, and also we have food in the back, so can everyone please line up if you want bonding. We have pork, chicken, and tofu.
Also, if you guys have any questions on the material covered today, I know it's a very theoretical basic workshop. Feel free to come up. Feel free to come up to us or hold on for a bit after you pass everyone food, and after that, you guys can ask us questions. All right. Thanks to everyone on Zoom as well.
Also, if you're not in the AI School channel, the AI School, please let me know. You can also ask questions there. Thank you.
All right. Thanks everybody on Zoom, guys. Hope you guys enjoyed it.